Okay, so today we're going to talk about wood construction. We're going to follow over the next 2 weeks a very similar process that we did when we looked at steel. So this week we're going to talk about the advantages and disadvantages of wood construction, when you would build with wood, and if you were doing a set of preliminary drawings, what sizes might you put on? Now, wood is interesting in that we have two major types of wood construction. There's conventional wood framing, which is the majority of what we're going to talk about in this lecture, but we're going to touch on mass timber, which is large-scale wood construction. Now, it is all the rage, I know, but what we're trying to do is cover the basics in this lecture and next week's lecture. And I can tell you that most architects in the industry don't even have good knowledge on mass timber construction. There are a few, but it's not a widespread knowledge base. So I would love to have a whole extra lecture just to talk about mass timber construction, and we'll touch on it, but it's not going to be the major focus of this lecture. So what are the advantages and disadvantages of wood? One of the big advantages of wood is that it's relatively cheap, especially for small-scale construction. It's cheap because of availability and just the ability to hire people to work on it. So that's partly lead time, meaning you can walk into a Home Depot yourself and buy wood to build your building. Again, I'm talking here about nominal construction or conventional wood construction. Mass timber is almost a whole separate thought process. And when I even started giving this lecture, mass timber was just a footnote. In the past 3 or 4 years, it has really exploded on the scene. And I'm trying to pigeonhole in a spot where it almost gets its own lecture topic. But there's not even enough basic information for it, really, to kind of have its own whole lecture segment. Fast erection. Once you've bought it, there's not much holding you back from building it. A house can be framed in a day if you have a team ready to go and build it. With that also comes available workforce. If I want to build a deck, I'll call up the girls and say, come help me build a deck, I'll provide pizza and beer, let's get it done. So most people have the skills to do wood construction. If not, you don't need many skills, and as long as there's someone on the team that knows what needs to be done, you can build that construction very quickly. Thermal properties. Wood has surprisingly good thermal properties. Not compared to insulation, for example, but compared to steel and concrete, wood has really good thermal properties. I have a cottage on Lake Nipissing. It's on an island. It's not fancy. It has no power. You need a boat to get to it. Very idyllic, but it's not convenient or easy. The construction is literally 2x6s all around the perimeter on edge. So what you see on the inside is the same piece of wood you see on the outside. There's just a thin coat of paint. It's tongue and grooved together. Would it pass any sort of modern day structural analysis based on the code? Nope, not a chance. But that bad boy has stood there for 60 some years, and a tornado went across my island 2 years ago, and the trees in a line came down 20 feet from the cottage. So the wind was intense, and the cottage has stood up. But the thermal properties are what is truly incredible. I mean, the structural capabilities of it are incredible too, but the thermal properties, I have hiked across the lake in the winter because I don't have a skidoo or anything like that. I've hiked the 7 kilometers across the lake to get to it. It has no power. It just has a wood stove, and I have gotten it so that you can sit in a t-shirt in front of the fireplace, where the only insulation is the fact that it is a 1.5 inch thick piece. It's actually a solid 2 inches, so it's not normal construction again. And that's been in like -25. The second it's windy though, the wind finds its way in all the little cracks and holes, and you cannot, even if it's 5 degrees, keep that place warm. So as long as the wood is sealed up, it has really good thermal properties. Treatment options. You can do a lot of things to wood to preserve it and protect it. It's inherently corrosion resistant. And I have fire resistant in that category. We're going to park that there for a second. And you see it says mass timber beside it. Look over here in disadvantages. Fire resistant, conventional lumber. We all know, and let's look at disadvantages here again, that wood is combustible. It will burn. If you've ever had a campfire, you know it will burn. But have you ever, just in your very small fire, taken a round log and set it on the fire? It will burn a little bit around the perimeter, and then it'll self-extinguish. That is why mass timber is over here in the advantages side. So there's two components to why mass timber is actually pretty darn fire resistant. It is big enough that when it burns, it will build up a layer of char that will actually act as an insulator from the fire, and it will help protect it. So you can't access the other wood that needs to burn. The second part is that it's so massive that as it burns, you're still left with structural capacity inside. I think the fire rating is wood burns at 1 inch an hour for framing. So over here in the disadvantages, if our lumber is a piece of lumber this big and it's only 1.5 inches wide, in a fire it's burning 1 inch on this side and 1 inch on this side. You've burnt away your structural material and you have nothing left. In mass timber, if you have something that's 6 inches wide, you burn away 1 hour on each side and you're left with a 3-inch thick piece of material. You've got structural capacity. And in a fire, you don't have to maintain full loading condition. You have, as the fire time increases, a decreased load you need to support. So you can be left with adequate structure in a fire event. The other part is that conventional framing, you often have a piece of plywood and studs or joists that are about 16 inches apart, so very often occurring. Fire does not do well without a re-radiating surface. So the reason we build our campfires with a bunch of little pieces stacked against each other is that you have a nice little spot where the fire can burn and bounce the heat off each other and continue to make that flame spread. Conventional houses are almost ideal for it without some sort of drywall fireproof protection against our joists. Mass timber, we have big elements, but there's not a lot in between there to kind of allow the fire to re-radiate against another surface. Other disadvantages in wood construction, it doesn't behave great for vibration. Connections. Connections are probably one of the biggest disadvantages of wood construction. We have to connect these two pieces of wood together. The only way to do it really is steel, although there's a big movement to make wood connections come back into style, so dowels, dovetailing. But you can imagine that for structural capacity, those are still the weak points of the system. Disadvantages are member sizes. They can be pretty large relative to the equivalent steel framing sizes. And we're going to look at examples of that next week, where we're actually going to compare relative sizes. Possible decay. So if you haven't done proper treatment options or preservation, you can end up with wood decay. So when would you use wood? And we're talking here about residential construction, or kind of standard construction, at least for this part right now. Residential houses, fantastic. Wood is great for farm buildings, temporary structures, special structures. We can do special structures. So we're talking like maybe institutions, museums, auditorium, maybe not an auditorium, sports complexes like rec centers out of wood, and that would be mass timber. And we used to only be able to build up to 4 stories with wood buildings, and that was the real limiting factor. In 2017, they changed the code, and in different spots across Canada, there's different limits, but right now it's at 6 stories. But that is going to change, and even right now, you can go higher than 6 stories if you apply under the alternative solutions portion of the building code and the building department. So you can do tall towers out of wood. So what are we talking about when we're talking about dimensional or nominal or conventional lumber member sizes? These would be our standard 2x material. So if you've gone into Home Depot and you've purchased some lumber, you're talking about nominal or dimensional lumber. So that would be 2x4, 2x6, 2x8, 2x10, 2x12, or your 4x4 or 6x6 solid material. We would often use joists and studs out of it at 16 inches on center. Beams and built-up beams, so that's where we screw multiple plies of this material together. Posts, so if we take a 4x4 or a built-up post where we screw multiple 2x4s or 2x6s together to make something equivalent. Take a note here of the dimensions. A 2x4, which is saying 2 inches by 4 inches, isn't actually 2 inches by 4 inches. It is actually 3.5 inches by 1.5 inches. Why the heck is that the case? Well, the milled size is 2 by 4 inches, and that's rough sawn and a little bit kind of grainy. If you rub your shirt on it, it would catch on it. And then they plane it down, and in that process, they take off, at least for a 2 by 4, a 1/4 inch on all sides. As we get into the larger dimensions, so a 2 by 10, we actually take off a little bit more off of the top and bottom as well. That's also where you get your smooth edges, your slightly rounded edges as well. You can get full-size lumber, so that would be an actual 2 by 4, an actual 2 by 6. You often have to go directly to a mill to get them. My dock at my cottage, we actually were up north and found a mill and actually got full-size lumber, so an actual 2 by 4 construction to build the system. Older construction was often done with full-size members. So the house I'm sitting in was built in the 1870s. All of the framing in it is full-size lumber. So the beams are a full 2 inches thick. Sometimes they're even kooky sizes, like they might even be 2.5. It depended on who was making the lumber and maybe even what mood they felt they were in that day. I-joists are an engineered product. These are ultimately designed by the supplier, but the depth can be indicated on the drawings by the base building engineer. These would be an alternative to regular joists. And regular joists, if we came back here, we would use 2 by 4, 2 by 6, 2 by 8, 2 by 10, 2 by 12 at 16 inches on center. We would instead do an I-joist to replace it. Again, typically at 16 inches on center, but this might be where we want to do conventional framing, but our spans are a little bit too long, or we have a few spots that don't work. We might bring in I-joists. You can see here, this is one supplier's chart down here. The depths are slightly different than your 2 by material. So instead of 9 1/4 inches, it's 9.5 inches. Instead of 11 1/4 inches, it's 11 7/8 inches. And then once we get into the larger sizes, it's actually 14 and actually 16 inches. The widths vary depending on the loading demands, but often the base building engineer would spec the depth that needs. So they do a preliminary design check, look at some loading tables, and see what depth we needed, and then the signed, stamped, and engineering drawings would actually come from the supplier. Plywood. Plywood are the big sheets that make the actual surface we walk on, or the actual wall surface that they would put a membrane on and protect us from the elements. It comes in a variety of thicknesses. You can see that in this drawing here, and this image here. The smaller thicknesses would often just be used for subfloor. We would rarely use those in a structural capacity. Floors and walls are usually 1/2 inch or 3/4 inch. Often we'd be talking, well, that's probably good enough information. They span 16 inches because the thing that supports them is at 16 inches. So our joists, or our I-joists, are at 16 inches on center, and our plywood is going to span 16 inches on center. Our studs, often 16 inches on center, and so that means our plywood under wind load would be spanning 16 inches. It can be 8 inches, 12 inches, 20 inches, or even 24 inches, but those are unusual. Probably 95% of the time, it's going to be 16 inches on center. If we needed kind of a replacement for a built-up beam, because our built-up beam didn't work or we couldn't get it long enough, but we basically wanted to stick to conventional framing, we could use LVL or PSL, which is an engineered wood product. This isn't typically what we're talking about when we talk about mass timber, although it might bridge the gap slightly. But often you would still use PSL and LVL in conventional construction applications. But it would be an engineered member within those applications. PSL is parallel strand lumber, which basically looks like you peeled off an apple and you have all of these strands and you kind of lay them out and more or less make them right. LVL is where you literally look like you're unpeeling the wood and then lay all of the strips kind of up against each other. And then they're infused with glue to bind them together. So that helps give us those longer spans, and we can get the widths that we need. Now, glulam, often mass timber construction. So you wouldn't typically use these in your conventional house situation. You wouldn't even use it lightly on a kind of rich person house isn't the right term, but unconventional residential construction. Glulam would typically show up in your institutional work or your large-scale construction projects. You can use it for beams or posts. The really cool thing is you can curve it because it is stacks of 2x material. So if we had a beam that looked like that, it really is a series of 2x material glued together. If you remember when we were looking at steel, the top and bottom extreme fibers were a really, really working hard point. Well, we can make our best lumber be at the top and bottom of these beams, and the stuff in the middle can really just transfer our shear loads. Remember, that was a big deal when we were looking at steel construction. So it gives us a lot of play here. Because we have essentially small members, we can curve them ahead of time and then glue them together. It's a lot easier to curve a small element than it is a big element. here are some typical glulam sizes that come straight out of the wood code. CLT, this is the one everybody wants to talk about. CLT is cross-laminated timber, or plywood on steroids. So literally we take 2x material and run them this way, and then 2x material and run them that way, and then 2x material and run them that way together, and glue them all together. So the exact same thing we did with plywood, but at a much bigger scale. Again, made from dimensional lumber. You would use this to replace the combination of joists and plywood deck, or the combination of studs and plywood shear walls. Instead of a clutter of small things, you have one big thing. It comes in 2 feet wide to 10 feet wide, and it can come up to 60 feet long. It can't span 60 feet. It would need supports somewhere in between it. And we'll look at sizing guidelines that show us kind of how far it can span. We can get it up to 20 inches thick, although that's getting pretty extreme. 3 to 5 layers of 2x material seems to be about the norm. This isn't anything for you to study. I just kind of wanted to show you kind of a cut-up opening of typical wood construction. You can see our joists at 16 inches on center. There's our wood floor. You can see studs at 16 inches on center with some sort of plywood framing on it. Don't worry about the let-in brace. We don't do that very often anymore, although it does still show up, and there is a slide in this where it shows one of those. Again, a jack post or a cripple stud beside a king post or a double stud for supporting a header or a lintel. Around a stair, we've got a double trimmer, a header, our stringer. Again, these aren't things I'm going to make you memorize, but if you're curious, here are some images that kind of just name off conventional wood construction. So let's talk about our sizing guidelines. Tongue and groove deck isn't used that often, but it does still show up. You'll see it a lot in pool decks or the roof for a pool, like a community center, for example. It behaves really well, and we're going to talk about this next week, but in high moisture conditions, even though wood doesn't do well in moisture, it does better than a steel deck. So it shows up quite often in those situations. It's available in 1.5 inch, 64 millimeters, and 89 millimeters. But similar to our steel deck, 38 millimeters or 1.5 inch is the most normal construction dimension that we would use. The sizing guideline is length divided by 40. So let's take a look at tongue and groove. If we had purlins at 1.6 meters center to center, what depth deck should we use? So we have a length of 1.6 meters or 1,600 millimeters. Our sizing guideline is 40. So length divided by 40 gives us 40 millimeters. I said our tongue and groove deck comes in... this is a typo here. That is a carryover from the steel one. So there we go. I've just updated that. I'll resave this, and let's keep going from this slide. So our 38 tongue and groove wood deck would be pretty good. Remember, our steel deck could span 2 meters. So it can span farther than our equivalent tongue and groove deck. The steel deck actually comes in 38 millimeters deep because when it came on the scene, and we're probably talking like the 30s and 40s, it set out to compete with tongue and groove deck. They wanted to be able to say, take your conventional construction and switch it out. Even though tongue and groove isn't normal for residential houses, you would use it in kind of bigger projects. Switch it out with our steel deck that can span farther. So that was really their selling point, that you didn't have to change anything else about the system. So even though it's the more common one now, and 38 millimeters seems kind of random for steel deck, it's because it was competing with our wood tongue and groove. Joists. Joists are a much more kind of common system supporting plywood. Our sizing guideline is L divided by 16. And remember, sizing guidelines are when things are normal. And normal is when our joists are supporting our plywood floor, and they normally come at 16 inches on center. So if we had joists that are spanning 2.75 meters or 2,750 millimeters, how deep do they need to be? So our sizing guideline is length divided by 16. We get 172 millimeters. A 2x8 is 184 millimeters deep. Remember, it's not 203, it's actually only 7.5 inches deep. So that is 184 millimeters. So it seems like if this is a regular conventional system, we would have 2x8s at 16 inches on center, or 38 by 184 at 400 center to center. And this would be a pretty common note to see on a set of drawings. So 2x8 at 16 inches on center, or 38 by 184. 2x8 joists are probably the most common. Again, it would depend on your span, but that's a pretty common kind of span length to have. Engineered joists perform just a little bit better than our conventional 2x material wood joists. So our sizing guideline, L over 18. We can go a little bit further with the same depth. So why wouldn't we just always use engineered I-joists? Well, what makes them economical is their repetition. So you need quite a few of them in a project to be worth it. So otherwise, your regular wood joists are going to be the cheaper option. And remember, cost is everything after you've met all the other criteria. So if we have I-joists that are spanning 7 meters, how deep can they be? Our sizing guideline is L divided by 18. So 7,000 divided by 18 is 384 millimeters. So that seems like our 406 millimeter deep or our 16-inch deep I-joist would be a good choice. Again, if we were supporting a typical plywood floor, we would want them at 16 inches on center. Again, we want our sizing guidelines to be in the world of normal, and normal is to have these joists or I-joists at 16 inches on center. So for this example, where we're spanning 7 meters, we'd want to call up 406 engineered joists at 400 center to center, or 16 inches center to center. As much as the 6 millimeters are different, we might say 16-inch engineered joists at 16 inches center to center. Beams. Again, anything that's bending is a beam, unless it's a truss. So our joists are technically beams, but they're ones that we're calling joists. Wood beams, or our lumber beams, are our built-up sections where we screw together multiple plies of wood. So just to give you a sense of what that looks like, we would have one 2x member screwed to another 2x member. And we would do 2 to 4 plies. You can even do up to 5 plies, but that's a little bit weird and we don't like to do it because it doesn't fit in a wall very easy. Our built-up beams are 2 to 4 plies of standard lumber. Columns can be built up or standard sizes. Engineered beams and girders, this is talking about glued and or laminated wood products like our LVL, PSL, or glue lam. So regular beams, L divided by 14. Engineered beams, so this would be our PSL, LVL, or glue lam, L divided by 16. Engineered girders, so that's a beam that just looks like it's working a little bit harder, would be L divided by 12. All right, now, I have a sizing guideline here that says beam width, depth divided by 2 to depth divided by 3. I hate the beam width sizing guidelines because people get hung up on them. This is more just an intent to help you figure out roughly how many plies you're going to need here. And it kind of gets annoying. Is it, are we using the, if it was a 2x8, are we using the 8-inch deep? Or are we using the 7.5 inches deep? Yeah, it's a sizing guideline. It is a rough approximation of the answer. I can tell you that if I'm going to give you a question on a quiz or an assignment, I would make sure that you only had one option that was within the realm of working. So if you get something ridiculous, that's probably not the answer. Do I have the same slide several times? I do. I'm going to stop this here and see what is going on, and then I'll come back to recording this. Okay, I sorted that out. For you guys, that was just a little blip, but there was just, I had 2 different versions that were almost the same, and I was combining them between this and the other course, and picking and choosing and making them kind of comprehensive and slightly better. So, no information different. I can't even remember if this was the slide I had already been showing you or not, but we've talked about this. Let's go on to the next slide. Let's do an example, or a few examples. We have a framing plan here. There's a lot of 2s in there, so I'm assuming it's a second floor of some sort. There's nothing that tells me that for sure, but convention is often that you would label second floor with 2s. It says the datum is 2.438 millimeters, so this datum is that much above the thing below it. What should be on the preliminary drawings for the plywood deck? So 2D01, spanning from here to here, but on something. 2J01, so that looks like this joist right here, and it says that they're at 16 inches on center, which makes sense because joists usually are. And we have 2J01 at 16 inches on center going from here to here. So there's a series of them all along there. And then it looks like 2J02 switches to I joists from here to here. So everything that's 16 inches on center in this zone is an I joist. Maybe they had a headroom issue or there's higher loads there. We don't know. We don't know the full context, but we're just putting something on the preliminary sizing drawings right now. They've asked us to size beams 2B01, so that's all of these beams, to 2B03. So 2B02, which looks like it's a relatively normal beam because it is picking up a series of joists. And 2B03 spans from CO4 to CO5. Oh, but look at this. Column above. So yeah, it's picking up joists. But we know that when we have something doing beyond just picking up joists, it's probably a girder. And this looks like a column above. So CA is shorthand for column above, which we've seen in our typical details, in our drawing, our look at basic structural drawings, and even last week in steel. So it looks like we need to think about that as a girder. It looks like 2B03 probably needs to be a girder. So the plywood deck, we know floors are typically 3/4 inch or 19 millimeter plywood with supports at 16 inches on center. There was just one. I'll write myself a note here. With supports at 16 inches on center. So on the drawings, we put 3/4 inch plywood, and that would be the end of it. We do know that that seems right because it's spanning 16 inches on center because the joists are at 16 inches on center. If we go back and look at that drawing, it looks like from here to here, or how far our joists are spanning, is 4 meters. Dave forgot to pick up a pumpkin, and it's pumpkin carving day at school tomorrow, and my kids need to count seeds and play with the pulp and guck, and I don't have a pumpkin, so I get to do that at some point. I don't even know how or where I'm going to find a pumpkin. Okay, sorry. Not your problem at all. Okay, so our 2J01 spanning 4 meters. The sizing guideline for joists was length divided by 16. So we take that 4 meters and divide it by 16, and we see that it needs to be, we need something that is 250 millimeters deep. Well, a 2 by 12 is 286 millimeters deep, because remember 2 by 12 is really only 11 1/4 inches deep. 11 1/4 inches is 286 millimeters. So the next biggest thing after 250 millimeters, 2 by 12s. So 2 by 12s at 16 inches center to center. It's a really good sizing choice, or a preliminary drawing sizing choice for 2J01. 2J02, they said, was an I joist. The length is still 4 meters. Our sizing guideline is 18. So 4 meters divided by 18 gives us 222 millimeters. Oh, well, we had I joists that were 241 or 240 millimeters deep. So that seems like a really good choice now. So maybe there was a headroom issue between those two sides of the building. Now the I joists are going to be slightly more expensive. So maybe they only wanted to use them in that discrete zone. So the 2 by 12s are cheaper than the I joists. So why wouldn't all the joists be 2J01 2 by 12 at 16 inches on center? Like I said, headroom issue possibly, and that 1 3/4 inch reduction might have been critical. We don't know, we just know we were asked to try to do both sizes. All right, 2B01. Let's start with regular dimensional lumber sizes, which is always the place to start because that is the cheapest. Let's go back and look at that drawing. 2B01, we have 4 of them, and they look like they're all 4 meters. So 4 meters, 4 meters, 4 meters, 4 meters. They're all the exact same. Our sizing guideline for a beam, which would be the thing that is picking up joists often, is 14. So our length divided by 14 gives us 286. Width, again, this is where I hate the sizing guidelines, because do we use 286 or do we use 302, which is our actual depth for a 2 by 12? Or do we use the 2, or do we do 1/2 or 1/3? All kinds, that's 4 different options we could calculate. Well, let's use the 286, because we know that that's the actual depth. And the width could be anywhere from 2 to 1/2 to 1/3 of that, so 143 to 95 millimeters wide. We know 2 by 12s are 38 by 286, or 1.5 inches thick by 11 1/4 inches deep. So it looks like our depth requirement, pretty darn good. And 3 plies of it would be 114, so somewhere between our 1/2 and our 1/3. Again, the width is such a crappy sizing guideline, but it does help you draw something reasonable. 2 plies would have been less than 95. 4 plies would have been greater than our 143. So I think going with the 3 plies seems like a really good choice. So it looks like our 2B01 should be 3 plies of 2 by 12s as our beam. So 3 plies of those 1.5 inch by 11 and a quarter inch deep beams screwed together to make one beam. 2BO2, it spanned a little bit further. 2BO2 spanned from column 3 to column 4, so it was 5.33 meters versus our 4 meters. Otherwise, it was the exact same. We want to start with regular lumber, because that's the cheapest. So our sizing guideline for a normal beam is our length divided by 14. We get 380. Our deepest conventional lumber depth is our 2x12, or 286 millimeters deep. So it looks like conventional framing or conventional lumber won't work here. But we don't want to switch to like steel or really big expensive glulam members. We do know that there is a alternative that we might turn to if regular lumber doesn't work, and that was PSL and LVL. So the sizing guideline for engineered wood for the same job was 16. So that same length of 5.33 meters divided by 16 gives us 333 PSL or LVL. We know that PSL and LVL both came in a 356 deep section. So now would we divide by 2 or 3? Again, this is yes, no, both, somewhere in between. So I took a look. I looked at it divided by 3, and I got 119. Well, 3 of the 45 by 356 LVLs, or 2 of the 68 by 356 PSLs seem like a really good choice. I wouldn't make you go that far with the PSLs and LVLs. I'd just get you to calculate the length. What's the difference between PSL and LVL? That's a good question. Not much. Different manufacturers make it different ways. They were both being invented around the same time. They have pros and cons for each of them, but they're pretty darn close to each other. One is slightly stiffer, and one is slightly stronger. So you can't just straight up interchange them from one another, but they're pretty darn close to each other. I have found that if I put LVLs on the drawing, I'll get a contractor that calls me and says, "You're crazy. Why would you ever use LVL? The only thing anyone ever uses is PSL." So the next project I'll do PSL, and that contractor will call me and say, "You're crazy. Why would you do PSL? No one ever does anything but LVL." So the answer is, it depends on where you are and who's building it, whether they prefer PSL or LVL. Now, the last one was our girder. Again, this one's double the length of our 2BO2, so I'm not even going to try regular lumber if it didn't work for the other one. And I have a deeper sizing criteria because this one's definitely a girder. So length, girder for engineered lumber was length divided by 12. So our 10.67 meters divided by 12 gives us 889. Well, there's no PSL or LVL of that size, so it would be a custom engineered wood glulam beam that's at least 889 millimeters deep. I gave you a list of different glulam members. I'm not going to make you memorize or look into those because as much as that's what's in the wood code, different fabricators might actually make different depths. They're very much custom members. Column C1 to C5. Well, it was height divided by 30. So 2,438 divided by 30 is 89. So that's the minimum dimension we need. A 4x4 is 89 by 89. That would work. Or we could do a built-up post or built-up column by doing 2x4s screwed together. 2 of them only gives us 76 millimeters wide. We need our minimum dimension to be 82. So we probably want to do 3 2x4s screwed together to give us our minimum dimension. Now, All of those columns, based on our sizing guidelines, exact same. But look, CO1 is taking just a tiny little corner of load. CO2 is taking a tributary area about like that. CO4 is taking half of 2BO3, which has got some column above, which has got some big load on it, and it's got a much bigger tributary area from the second floor. So we can see at a glance that these shouldn't be the same thing, but for our preliminary sizing guidelines, this would be a pretty good place to start. So now let's just look at wood construction. That's the hard part done. Our sizing guidelines are done. Let's just look at, I say typical, but we're going to start with not typical whatsoever, but we'll get into typical. So this is just old wood construction. Wood construction has been around for so long that there are lots of examples of kind of existing wood construction. If you went into my basement, if you could get by the spiders, you would see that it didn't look quite like this, but it would be somewhat similar. It would be slightly older construction with larger size, full-size dimensional lumber, and my floor is actually tongue and groove flooring. One of the things I like about this log construction is the gaps here. So obviously there's some gaps because we have a round thing connecting to a round thing, so they come and touch at only a very small point. But wood, we're going to talk next week about how wood shrinks when it cures or dries. And because of that, we can end up with gaps. And they have shoved oakum or some sort of sealing material in here to help seal up the wood. This is really old wood construction, just to show you how long it's been around. And if it's done well, it can really stand the test of time. So here's another image of conventional framing. You can zoom in on this by looking at the PowerPoint if you want. I'm not going to get caught up on the nomenclature of these things. Maybe think about the fact that we have diaphragms on our floors and shear walls. So this would be our plywood on our wall and plywood on our ceiling or our floor. Here is a floor or deck framing. I'm really cold. I'm just going to go turn up my heat. Okay, so this is conventional floor or deck framing. You can see that we have joists that are probably 16 inches on center. You can see the plywood sitting here getting ready to go on it. So probably not a deck, probably going to be a bunkie or an enclosed building of some sort because plywood doesn't do very well outside. You can see that the joists frame into a beam. And look, the tops of them are all at the same plane. So that is an option where you hang your joists off of your beams. Sorry, I'm not being weird. I'm tucking my blanket in. Here is another deck or floor plan. Again, we've got elements at 16 inches on center. They have a double 2x8 beam here. So you can see that's 2 plies of 2x8. You remember last week we talked about steel when it is in bending, the top cord tends to pop out sideways because of its unbraced length. What we do for wood is we shove blocking in there just to make sure that it can't kind of pop out sideways. Here's another image. Now this one's slightly different. You can see that they've got a beam dropped below and the joists frame across the top. That is a legitimate, normal style of construction in wood. I don't see it happen that often, unless you're talking about decks, for example. The way I often build decks is I will do a grid of 4x4 material, and then a grid of 4x4 material, and then my deck boards. So that might be the only time I would draw joists kind of going on top of something. That said, it is a legitimate way to do it. You might see it more maybe in builder style construction if there's headroom, but often we're trying to maximize headroom, so we don't do it that often. You can see that instead of just blocking of 2x material, they've actually taken little strips and made almost little braced elements, and they've framed around an opening here. Here is one with eye joists. So you can see that we've got a girder or a beam here with floor sheathing or a diaphragm on it, and at 16 inches on center, we've got eye joists that are spanning from the concrete wall to the beam, and then from the beam to, I'm assuming, a concrete wall behind us. A stud wall. We often have an infill of wall for structural walls here. Rather than large members spanning, if we have a wall, we will use it everywhere. So we would have our studs at 16 inches on center. If it is a shear wall, we'd put plywood on the surface. Otherwise, we'd probably just put drywall on it. You can see that this is over the door. We'd often call that a lintel or a header. And the same way we did with our floor joists, to prevent our studs from buckling in the weak axes, we'll often put blocking in between the elements. It needs to be somewhere around the middle, and they make it so that it's easy to nail these things into each other so that your nails aren't hitting. You can see joists down here that look like they're at about 16 inches on center, and a ceiling joist up here, which are about 16 inches on center. And look at this. They've tried to line them up with roughly where the studs are, too. You don't have to, but it's good practice. Here's an actual look at a stud wall, so very similar to what we were just looking at. There's a lintel over the window opening. We've got our studs. We've got our shear wall. We've got eye joists spanning from something back here to this. And then look at this. We've got what looks to be a cantilever here, something going out to pick up an overhang there. Double stud wall, not that common. I had this slide in here for years, and then when I bought this house, there's an addition on it that was done. The addition was done in 2005, and we built a deck in the back, and when we busted out the wall where there was a window to be able to get to where the deck was, we saw that we had a double stud wall. And so the idea here is rather than just have your regular 2x6 studs, that is one end being the inside of the wall and one end being the other side. So instead of just this being your stud wall, they do this. And the idea is that you don't have any cold bridging. So you insulate through all of that. Now that said, if you're doing a building with a ton of windows, that effort isn't going to make your big difference. All of your cold is coming in through, even with the best windows, most of your cold is coming in through the windows. If you've got more than 25% of your wall area as a window, just do a regular stud. I mean, I get it, this is cool, but it is a lot of material that might not be doing that much for you. Here's a long lintel. So you can see that we've got a big stud here and studs here, and a continuous lintel, so that this is just a little bit of infill right here. Wood joists with metal hangers. So these are it looks like a 2x8 with a joist hanger connected into the side of this LVL beam, and the tops all align. Here's one where joists come across and sit on top of the beam. They lap past each other and screw into each other with blocking in between. So you can see the beam down here. If you have joists at your ground floor framing into the side of a foundation wall, what we often do is, rather than try to connect each joist into the concrete wall, which becomes a bit of a headache, we try to make it just like framing into wood. So what we do is, around the perimeter, we put a ledger beam, or that's just a piece of 2x whatever that we anchor into the wall with some regularity. So 8 to 24 inches on center, we might put these sleeve anchors to screw the ledger into the side of the foundation wall. So you can see that there's a ledger screwed in, and then the joists with the joist hanger, and then decking on top. Here are some different joist hangers. You can have base mount or top mount. I joist with holes. You can do this. You need the supplier to design it and say that it's okay. You can do it. But again, remember the rule for steel: middle third, middle third. You can see that they went past the middle third here, so this had to be engineered. But if you keep your opening in the middle third and middle third of the length, you don't even need to worry about reinforcing usually, or a check. It'll probably just work. Roof trusses. I don't get hung up on truss names. I think the engineering will just shake out. How many configurations? The reason why I don't get hung up on names: how many configurations of trusses are there? Unlimited. You outline the profile, and we can come up with the infill that is the most economical and most engineering efficient. So here are a few names with a few different types, but you can see you can start to get into all kinds of kooky things. So they are custom made, designed to specific criteria, and there are an unlimited amount of configurations. So here are some kind of being brought to the site and getting ready to be installed. Again, look though, they are supporting plywood, so 16 inches on center. Here are some roof trusses getting ready to be installed. They must have 2 different roof heights. Look at this one at the end. The reason the roof trusses work so great is we follow the best line of support. But at the end, we need our plywood to go on a surface that is going to only span 16 inches. So we need these elements for our end walls to be every 16 inches. And then most likely this doesn't need to be an engineered truss in the same way, because below it you will have studs at 16 inches on center. Here's a built-up beam with a splice. We don't like to do this. What's happening here is this is still only technically a 2-ply beam. So why would you bother doing this? Well, if you were limited on length, for example, of available members, maybe you spliced if you were limited in the length of material you had, maybe you spliced this one here, and this one here, so that at any given moment you have 2 fully functional plies thick, but you could span it further than you could 2 plies. If you needed 3 plies, you could not have a splice in that element. Built-up beam sections. I want to change the order of those two slides. So you're going to see those two slides in a different order because the splice is the unusual one and these are more of the normal ones. So I kind of want this one to come first. So here is a built-up beam section. So this is what I'm talking about when we take like 3 plies of 2 by 12, for example. That would look something like this, where we have, and the engineer would reference a screw pattern of some sort. If you looked at the typical details for wood, you would see that we have typical screw patterns called up on what you need to do to make a 3-ply, 2 by whatever member. You can start to do plies with bigger members. So this would be like the multiple ply LVL or PSL we looked at, for example. And then the spacing requirements for screws are very, very particular. Here is an LVL beam framing into an LVL beam. So this would probably be a beam, and this one's probably a girder. Here again, we have joists framing into a beam, making this one a girder that I'm assuming is a shorter span than this one. A flitch beam. A flitch beam is something we employ when we can't get our wood beam to work and we're running out of options. So if we sized a member and we found, like we went through and did we were limited on headroom, so we couldn't go deeper, and we found we needed 4 plies of engineered material. So the engineered material isn't 1.5 inches thick, it's 1 3/4 inches typically, or the LVL is. We would find that it was 7 inches thick. Well, if we needed to fit in our a 6-inch wall assembly, we'd have this little bump out. So if we combined the beam and the steel, so each of these is doing part of the job of carrying some of the load. And in 2 weeks, we're going to talk about load sharing versus composite materials. We are able to get rid of 1 whole ply of wood and replace it with these 2 thin plies of steel. Why wouldn't we just make more plies out of steel? Because it's more expensive. And we're doing a wood building here, so we're trying to go with the cheapest option available. Here are some glulam beams connecting into a glulam girder. Look at this, you can see the connections. So this starts to be where our connections really start to be visible. I had said connections were an important part of the design aspect and they were a disadvantage for wood construction. And that was true even like for our built-up beams, for example, but you can really start to see it here. Curved glulam. So each of these individual plies, before they assembled this glulam, were curved individually, and then it was glued together. More curved glulam. So here we have a shear wall. We're going to do a lecture on lateral load resisting systems, and you're going to see these slides again. So mostly I just want you to get used to the terminology. But our lateral load resisting system is the thing that helps our building not tip over or slide away in wind or earthquake loads. So you can see here, this is one of the best images to help describe what a lateral load resisting system is doing. We have wind or quake pushing on our system, and you can see that this lifts up, this slides over, it actually starts to come down here, and our panels bust apart, and this fails at the connections. If we put our plywood shear wall on it, so it's being braced every 16 inches from our studs, our plywood does the work of our lateral load resisting system. So for wood, it's often shear walls. We need to hold this down here. That's to stop it from tipping up. We need anchors here to stop it from sliding. So here is a tie down. Is that? Yeah. So you can see here we have different options on how we can do a tie down. These ones here are actually products that you can get from Simpson Strong Tie, and you can see how that connection looks right here. If you were going from wood floor to wood floor, you might actually do strapping connecting those things. Just another image of a wood shear wall. You can actually buy product wood shear walls. So this would be the Simpson Strong Tie prefab panels. I've found it a little bit hard to get them to work. Trying to fit within the exact dimensions I have for the loads I've had has been a bit of a struggle. The nice thing is if you give them the loads that come in on it, they do the design. There's a second part to our lateral load resisting system, and that's what stops our floor from kind of skewing in plan. So we would call the plywood floor our diaphragm system. And there are requirements for how these are connected and how often our screws need to connect to make it meet our diaphragm requirements. Another type of lateral system is we might brace the corners here. So essentially we're making a moment connection. If you guys remember in our drawings lecture, I said our moment connections are drawn as little triangles. Well, that's because that's essentially what we're doing, is we're forcing it to act like a little triangle, and we're forcing these two members to remain at a 90-degree angle to each other, even when there's a lateral load on the system. You could do a kind of let-in or built-in braced frame element, less common. And on a mass timber building here, you can see they actually use wet wood elements as the lateral load resisting system. Again, connections become a big part of that system. Moment frames. Do we do moment frames in wood? Whew. We can. It's expensive. They don't work as well. And they're less stiff. And I'm going to show you a study of that in our last lecture. But it can be done. It is not where you would start. You would do it as a last resort. So this is an infill project. This was by architect Drew Mandel, and it was his own home. So you can see that, you imagine if you have a stairwell here, you're not left with much room for your building. If you want windows, you don't really have any spot for lateral load resisting systems in this direction, which is also the direction you have the most amount of wind blowing on your building. Yes, I know these buildings are here, but we have to assume they might not be there at some point. So conventional shear walls didn't work. We suggested steel and braced frames, but that didn't work with the layout. So eventually what ended up happening was a series of, this is a plan drawing, a series of moment frames. Now, normally our joists and studs are every 16 inches. To get this to work, they needed to be every 8 inches. And then, if I draw this in elevation, there's the ground floor, first floor, second floor, and roof. So if this is the plan, every one of those locations needed a ridiculous amount of specialty screws. I think it was like 12 specialty screws that were expensive, like not pennies, like dollars per screw, and 12 of them per connection, 6 times per frame, and these frames were every 8 inches. It worked. It was the only way they could build the house. So it isn't where we would have started, but it's where we ended up because there was no other option. Even still, I remember talking to Drew just after Hurricane Sandy hit, and he laid in bed. He could feel his house moving, and he just kept saying, I know stiffness is not related to strength. I know stiffness is not related to strength. I know stiffness is not related to strength. And I'm going to show you some slides that really illustrate that very well in our lateral load resisting system lecture. But basically, even once we got it strong enough, it wasn't as stiff as any of the other options might have been. So we don't do moment frames lightly. We especially don't do moment frames lightly in wood. Connectors. Connectors start to steal the show in wood construction. If you think of your kind of classic Douglas fir construction in BC, we've got large scale elements with large black steel connectors. That's because once they were big enough, architects realized, well, we might as well make them look good and even showcase them slightly. So that's your kind of your iconic imagery of your classic large scale wood construction. We're getting better at it. As more and more people are moving to wood construction, we're getting better at detailing hidden connections, but there's still such the governing part of the design that sometimes it's hard to do that. Here's a situation where they might not have thought about hiding the connections as well as maybe they could have, to the point that it really starts to take over kind of what the imagery of this system is. Base connectors for wood. Often for wood, we don't want our wood to touch the concrete. Concrete can wick water a little bit, and so can wood. So if we have the wood touching the concrete doesn't get hurt by the water, but the wood will. So if the concrete wicks the water and then the wood wicks the water, that's where you're going to get rot. So we'll often do a slight standoff with a steel connector for wood in basements. A steel to wood connection is not recommended. I always say, if you have steel, chase it down through the building with steel. Wood shrinks, and when you've got all wood moving together, you've got connectors that help deal with that. But the steel is often usually there because it's supporting something that is precious or highly susceptible to deflection. So maybe there's a masonry wall on this, or a fireplace, for example. As this wood shrinks, and we're just talking a couple millimeters, this beam will drop down with it, and you'll end up with severe cracking in your masonry. So I do not recommend supporting steel beams with wood columns. You can do unique structures. This is the project I did in 2008, where this is actually a reciprocal frame. So each one of these is individual members, and the whole system isn't stable until it's entirely complete. In fact, Dave and I did a lecture for the Australian Wood Council last week with 500 virtual attendees talking about reciprocal frames. Wood bridges, so you can see this is glue lam here, and look, they needed to splice together connections here. So the connections start to really read strongly in the system. Just more bridges. This is a cool project. This is one I did kind of early in my career. This is the Canadian Peace Bridge Plaza. Originally, it kind of was intended to be a reciprocal frame, beyond what you guys need to know. In the end, we came up with kind of major girders supporting smaller beams that then supported smaller infill panels with a tongue and groove system spanning over it. So we needed the kind of this kind of set, the strength and depth of our tongue and groove was our maximum span. Mass timber is coming into play more and more. NLT, or nail laminated timber, as a floor or a roof system was big in the 40s, 50s, 60s. A lot of wood arenas used NLT. So instead of members on flat, or a whole bunch of tongue and groove members kind of like this side by side, they turned them up like this and did a whole bunch side by side. So this is nail laminated timber, where these are nailed together. You can even call, sometimes they even call it dowel laminated timber, where we have eliminated nails and used dowels instead. There's a big resurgence in this. I actually have a major project kind of that just is starting construction in 2 weeks using NLT. Now, the problem with NLT is fire rating, vibration, some sound carrying, and often we have in-floor heating. So usually we need a concrete topping anyway. So often there would be a concrete topping on top of this NLT system. That lends us out to a few other kind of methods of construction that I'll show you in a few minutes. So here's the underside of an NLT system on a wood frame system where we've got major beams. And you can see down here that the concrete, or the wood's been held up with some down here. There's going to be a concrete topping on this floor. You can see that it's framed out for a concrete topping to go on it. If you don't have a concrete topping, you can start to stagger those NLT panels relative to each other and get a really beautiful curved system. This was done by Fast and Epp, who they've almost literally written the book on NLT. Most of their staff are contributing writers to the code or the guideline for designing with NLT. CLT, you can do it in floors or walls. You can see one of the nice things about it is that it can be shop fabricated. One of the hard things is you need to really look at construction loads on it, because you can imagine that this might be the governing load case. So here are some CLT walls and floors being installed. This one, really, really beautiful system, showing CLT floors and roofs and walls. Basically the entire system is CLT. This is the one that might possibly make us rich. This is, the name has changed. It's not Bubble Lamb now, because we're actually patenting something. But we're not good at it, so you guys already know. But there's lots of great things about this. We said that you often need a concrete topping anyway, and at that point making things composite starts to lend itself really well. Composite, something we're going to talk about next week. That's basically when you force things to glue themselves together to work together, versus load sharing, where they just kind of work side by side, even though they're on top of each other. To get concrete and wood to work together, you need quite a bit of concrete, or you need some depth to that concrete. Well, this puts voids in the concrete to eliminate a bunch of the concrete, but have the concrete and the wood work compositely together so that you get a really good, efficient system. And remember, you often need that concrete anyway, even in your fully wood systems. Where can we go with wood? Oh, baby, we can go so high. We can do such amazing things with wood. This is really the cusp of what we're talking about in the world with mass timber construction. Under alternative solutions, there's not really a limit on how high we can build with wood construction. I know that Blackwell has several projects on the go that if they were built right now, they would be the tallest wood buildings in the world. But I think almost every firm in Canada and Europe might have one of those projects kind of on the books. So like a ridiculous number of mass timber kind of, this is the movement, this is the future. Is it cheaper? Not always, but it's also innovative. So innovation is not usually the cheapest. Is it smart and sustainable and responsible? Definitely. Are we going to get better at it? Yeah, for sure. And pretty soon we're going to see this is a large portion of our large-scale construction projects. So these are just a few that I wanted to show you to kind of give you an idea of what's coming in the future. This is the one where I actually did this steel project here, and at the time had to design it because the basement for these two is connected. And in fact, the elevator for this is actually the elevator core, part of the elevator core for the tower. So when I designed the elevator core for this and the foundations, this was an unknown tower. U of T said, okay, assume it's some, many stories buildings. But you can imagine where the braces go, where the core goes, what the plan is, what the layout could change absolutely everything. So I had to get really creative to not limit future construction options. And I gotta say, when I did it, wood construction wasn't even on my radar as a possibility. I designed these foundations in 2011 with another colleague of mine at Blackwell. And we did not anticipate that it was going to be a wood building going in on top of it. Luckily, it's the same design team that's handling the process. So we were able to look at it and kind of quantify what it would take to make this a wood building when we started this design process in 2016, 2017. And it's going to happen. Contract documents are starting up any day. And so future construction, it's probably going to happen in the next few years. Here are a few more. This was a competition for George Brown, the Arbor project. Blackwell's project was this one, and I did the preliminary design for it. There was a few great options. This was the winning option. Unfortunately, Blackwell couldn't be on all the teams, so it was a different engineer. It might be Fastenap, in fact, kind of our favorite wood engineering pals that we've collaborated with and kind of discuss ideas with. I think this was Fastenap win on that one. But you can see wood is the way we're going on these projects. CAMH, another wood project. North Bay is where actually the Wood Solutions program is based out of North Bay. And they have one of the largest wood buildings in the world on the books being developed, hoping to be built soon. So what are the takeaway tips for you guys based on wood? Well, you should know the advantages and disadvantages of wood construction, keeping in mind that one of them is a different thing, whether you're talking about residential construction or mass timber construction. You should have a good idea of when wood is a really good choice. It doesn't mean it's the only choice, but when it's a good choice. You should be able to recognize basic wood construction, so 2-bys, built-up beams, lintels, studs, posts, shear walls, plywood floors. You should be able to do preliminary sizing of wood construction. And you should understand that wood design is evolving, and it is cool. It is the future. It is what is happening. Dave, my husband, recently wrote an article in Canadian Architecture on wood construction, and that was kind of published, and people have been contacting us worldwide for him to talk and be able to use his images kind of to show what wood construction can be for mass timber. If you get the opportunity, find some of his lectures if you're interested in this, and kind of follow along on some of the webinars that might come up, or ones that have happened in the past. If you can kind of view past webinars, seminars, kind of really, really cool, innovative stuff happening in mass timber construction. Okay, next week we will talk about actual design of wood elements, very similar to what we did with steel. How can we size the actual element we need? How can we go beyond our preliminary sizing? So we'll talk about that next week, team.